So, are there any questions about the paper? Yes.
When you're like giving the figures sort of an orientation on the paper, I know I emailed you about this earlier.
Oh, about like the placement?
Yeah, the placement. I'm just having trouble because they're just all going to the end, pretty much.
Yeah, you know, that's hard. I know it's hard to do. And my advice, I think the advice that I gave you at the beginning was wait until the end when you have lots of text, and then try to place them. And the thing of it is that these figures are floating elements. So tech figures out where to put them based on your hints, whether they belong at the top of the page, the bottom of the page, or whether they occupy a full page. And so the only way that you can change the placement of it is to cut and paste your flowing text either above or below where you say to put the figure, and then tech will try to put it close to where that is. But it's difficult. And if they all get I think I gave you a guideline. I said don't have them all at the end, but if it's unavoidable, yeah, I don't want us to spend huge amounts of time trying to get that done.
There's actually a pretty good way of doing it. If you do bash clear page, it'll make sure that all the figures that are above it are placed before the clear page.
Oh, what's the command for that?
Bash clear page, and also creates
Like this? CLEARPAGE, all one word?
Whichever one is the one you're meant to use for like sections, bash section, or is it just normal slash?
No, it's bash.
Okay, yeah, so then it's bash clear page.
Yeah.
Clear page. And then you can also do bash big break, which gives you like a space between two lines.
Yeah, sometimes I use bash page. Or is it page or new page? I don't remember now. I better not put it up.
Clear page puts a page break and also updates where the picture should be.
Yeah. Okay, so there's a tip. Yeah.
Does it matter? Like, I'm having problems with like making the graph look scaled properly. Because there's problems sometimes, like, I think when I took the PDF, it might have been like, basically like a rectangle, so like if I was trying to put two together and squish it into like two squares, it like looks a little funny and goes like a little bit past the header. Okay.
Yeah, let's not spend an inordinate amount of time making it look absolutely perfect. So, but there is a scale, when you include figures, there is a scale.
With the scale, and it did help in some cases, and then
Yeah.
it would like skew one.
Yeah.
The other one would look normal. I don't know, I just need to
Yeah.
Like, I wanted to know worst case scenario.
No, you're fine. It's fine. Yeah, let's not worry about it. But I'll have to say, that the manuscript that I'm posting, all that's LaTeX, Z-LaTeX. And it looks, but it takes a long time. It takes a while to figure out how to do everything all just right. And I know for a first cut, it's hard. I know it is difficult, because basically what you're doing is you are having the tech code. It's like your source code, and your printed paper is the object code, and it's a compiler, and there's syntax, and you have syntax errors, and and then trying to get it to do what you want it to do is not always easy. And it's a steep learning curve, but I'm telling you, it's worth it. Man, once you get your document the way you want it, it's a beautiful typesetting for math and technical stuff. So math, physics, and computer science all heavily use tech. So that's why I think it's a good tool for you to learn. Any more questions before we go on? Okay, so at the end of class on Friday, I think it was, we had introduced the list, the by-tree L project, which is the linked version of the binary tree, and we had done these pre-order, in-order, and post-order traversals, and we looked at the code for the pre-order traversal. So now let's take a look at let's do some code walkthroughs and take a look at how some of these operations work. The first one is very easy in figure 8.8. It's is empty. So is empty is very simple. There's only a tree version of it, and as all it does is the by tree L : is empty. It has in its as an attribute a root, and as all it does is it just returns _root == null pointer. So if the root isn't the null pointer, then it's empty, and if it's not, it's not. Yeah? So that's, and obviously you're not going to do, what would be an amateurish way to do this? If _root == null pointer, then return true, else return false. All right? So don't do that. Slightly better, but still not as good, is return _root == null pointer, question mark, true, false. Okay, but still, this is even better than that. Okay. And now, one that did not get exercised in the, for the user in the main program is left is empty. So there's a left is empty and there's a right is empty, because sometimes these algorithms are going to need to test whether the left is empty. So what happens is there's a precondition. If root == a null pointer, then the tree doesn't have a left. So you can't test the left subtree of an empty tree. So that implements the precondition there. Otherwise, what do we return? So you remember it's _root arrow left. So how did that work? Remember it was like this in figure 8.3. So my by tree dot _root is a pointer to a node, and then the left, it's my by tree dot _root arrow left is the left pointer of the node to which it points. So that's how we test. So we return _root arrow left == null pointer. Everybody good with that? That's just a little short little one-liner. And I think we did demo this one. Root returns the root value, returns type T. But again, if the tree is empty, it doesn't have a root, okay, a root value, so we implement the precondition like this. So what happens, this is an example of that case where there is a tree version and a node version. Yeah, this is where we have a tree version and a node version of root. And so what happens is the tree version checks to see if it's an empty tree, and if it is an empty tree, it implements the precondition restriction. Otherwise, what it does is it calls the node version. Are you with me? It calls the node version of root, and then the node, because _root is a pointer to a node, so root arrow root parentheses is a call to the node version, and then the node version does what? Just returns _data, because what? Because in the environment of a node has an _data and an _left and an _right. Oh, now this next one is num nodes, number of nodes. Now here, I don't have a picture of this, I think, but look. Suppose this is a tree that's not empty. So this could be like 50, and this. Now, and this represents some subtree. And this represents, so this is L and this is R. This is the left subtree and this is the right subtree. And the question is, how many nodes are in this tree? Well, look, if it's an empty tree, so if this is the null pointer, then how many nodes are in the tree? 0, so it returns 0. Are you with me? Otherwise, what does it do? It calls the what? The num nodes method of a node. It calls the num nodes method for a node, and it does _root arrow num nodes. So now the code for it being here in this node. Now the question is, how many nodes are there in this tree? Well, there's obviously what? There's 1 for this plus what? However many are in here plus what? However many are in here, right? Does everybody see how that works recursively? Okay? But now here's the thing. This is the linked list version, so we don't know. This could be empty. I mean, this could be the null pointer. Are you with me? This could be nil. So look how we guard it. We say, so int result gets 1. If underscore left is not equal to the null pointer, now what do we know? We know that underscore left actually does what? Points to a node. You see how that guards it? That guards us not having a null pointer reference. Always with these linked ones, you guard. Are you with me? We guard it. So if underscore left is not equal to null pointer, result gets result plus underscore left arrow num nodes. So then that recursively calls however many nodes are in this one. And then it checks to see if this one is empty, and if this one's empty, it doesn't do anything to result. But otherwise, what does it do? It makes a recursive call to this and right arrow num nodes, and it adds that to result, and then in the end, the result contains 1 plus however many nodes are in this one plus however many nodes are in that one. Boom. Yeah? Does everybody see how that works? And notice how you guard. Notice before you ever use, anytime you ever do a pointer, arrow, something, look in your code to see if you've guarded against it being nil. See, that's just a technique. Now, in figure 8.10, we have some definitions of some quantities that are used, that some of these functions compute. One of these, the one that's shown on the right-hand side of each tree, is the height. So notice that in part A of figure 8.10, it's a binary. We have a binary tree that only consists of just one node, and that's 60. And so that node is both the root and it's also a leaf. And we are going to define the height of that tree to be 1. And then in part B, there is a binary tree with a root of 40 and a left child of 20 and a right child of 65, which in turn has a left child of 30. And the height of that one is 3. And then in part C, the height is 5. So it's how many levels down you go. Now let me hasten to add that the height of a binary tree is not, the definition of the height of a binary tree is not consistent between authors. It depends on the book. And in fact, this definition of height is the same one that's used in our Gries and Schneider book that we used in discrete structures. All right, but it's actually not the most common one. You know, for example, if you take a look at part B, it actually looks like what's an alternate way to define the height? Instead of that height being 3, it's like what? 2. Like 2 stories high. You see what I mean? It's like, so with some authors, they define the height as how many levels you have to go up to get to the top. And so they would define that height to be 2, and they would define the height in part C to be 4.
And A would be negative?
And A, well no, and then actually that's a good point. So then what would A be? The height would be 0. But I don't like that definition, and neither did Gries and Schneider. Because using that definition, what's the height of the empty tree?
-1.
It would be -1, and that doesn't seem right. It seems like the height of the empty tree should be 0. So when we are talking about height, we're talking about how many nodes. We're talking about not how many jumps there are between nodes, but we're talking about how many nodes there are in the levels on the way down. Are you with me on this? And you know, when we developed all these algorithms and stuff, we had to deal with that difference, and we've decided to go this way. But it's actually, most people do it the other way. Not sure why, because this seems more natural to me. But some people do it this way. And then a leaf is a node with no children. So in part B, what are the leaves? Oh, it says there. 20 and 30. And in part C, the leaves are 90, 40, 50, and 75. So everybody sees, so that's the definition of height, definition of leaves. An internal node is a node that is not a leaf. And so the internal nodes in part B are 40 and 65. So the number of leaves plus the number of internal nodes is the number of nodes, right? Because a node is either internal or a leaf. Now, in figure 8.11 is, let's do a little code walkthrough of this. This is max. So the maximum, it returns, I think we demoed, did we demo this? Maybe not. Oh, this might be in the supplementary demo one. And then, so what happens, in order for a tree to have a max, it can't be empty. So the root version of max checks to see if root equals null pointer. If it is, it violates the precondition, and so it implements the precondition. Otherwise, it calls the node version of max. Now watch this. This code evolved over a long period of time. Now let me say, the third goal of this course is C++ programming, right? We all know that now. Okay? And let me say that there is a little C++ gotcha that is really tricky and it's obscure, and I don't want to go into the details of it, but this first line in the node version of max sets up a temporary variable called data temp, and the reason is because what max returns is a constant reference to t. You see, it says for this max function, what does it return? It returns a what? A t const ampersand. So it's returning a reference to t. All right? But now what is a reference? A reference is a what? Well, is an address. And what's a pointer? A pointer is an address. And there are some restrictions on using t const ampersand, and you can't do it. To do what we want to do in this code that follows, we need to use a pointer instead of a constant reference. And so this first line here is t, so look, what does it say? It says t const asterisk data temp. So what is data temp? It is a what to a what? A pointer to a t. Are you with me? Now what is a pointer? It's an address. And so do you see it gets ampersand underscore data. Now what is underscore data? That's the data part of this, that's the underscore data part of this non-empty node. I mean of this node. The only nodes we have are non-empty nodes. There are no empty nodes in the list L. Are you with me? So it's the data. So do you see that that's consistent with the types? It's setting one address to another address. And now what we do, and the reason for that is some obscure C++ thing. And now what we do is we use data temp now instead of using underscore data. That's the reason we do this, is so we can use data temp, because we can't use underscore data this way in the rest of this code. But what is data temp? It is a what to a what? It's a pointer to a t. So look what we do. We define, now what is left max? What is its type? It's also a what? A pointer to a t. So what we do is we say if left equals null pointer, then what is underscore left max? It's data temp. You see? So here, if there is no max over here, then what are we doing? We are setting left max to the what? To this. Do you see? But if there is a tree, if this is non-empty, you know, if this does have a max, then what are we doing? We're calling it recursively and returning the max of this to be left max. You see, this is calling underscore left arrow max recursively. But basically what we're doing is we're saying, okay, so the max, if this is empty, then the max is just this one. If it's not empty, then the max is the max of this. All right, and then we're doing similarly for the right. So that was it's only for the right. So now what we're saying is, if this is empty, then right max is just this data. Otherwise, this is the what? Otherwise, right max is the what? It is the max of this tree, of this right tree. And now look what we have on the third line, on the next line. We have nested trinary operator. Are you with me? But why not? You see what we're saying? So look, there's one big trinary operator. So what's the first thing we check? We check if what? So we're saying return. So now what do we check? Star left max greater than star right max? What is that saying? Left max is what? Is bigger. So what do? We do this penultimate line. Otherwise, what do we return? The last line. Are you with me? And you're following this logic? And so now let's look at the penultimate line. So if left max is bigger than right max, then what do we have to compare? Left max with what? With the temp. All right? And then if left max is greater than data temp, then star left max is what we return. Otherwise what? Star data temp is what we return. Okay, so let's take a look at methods for construction and insertion. So in figure 8.12, we have a copy constructor is disabled. We have insert. I think we demoed insert root, right? That's how you build a tree. You make it with one root value. So precondition, this tree is empty. Postcondition, this tree has one root node containing data, so we give it data. And then set root, I think we did set root. That just changes the value of the root value. So the precondition is the tree is not empty. The postcondition is the root element of this tree is changed to data. And then I think we also did set left and set right, did we not? I'm pretty sure we did that. I'm pretty sure we demoed that. So set left is, the precondition is that this tree is not empty. Because, if we're going to set the left, we've got to have a left to set, right? And the postcondition is the left child of this tree is subtree, and the old left child of this tree is deallocated. And furthermore, once we set it to that, remember this is a cut set left, not a what? Copy set left. So it doesn't make a copy of it, it actually cuts it out, which means that what used to be subtree is empty. So subtree is the empty tree, is another postcondition. And similarly for set right. All right? And then for the rest of the figure, we have operator gets, and so that's the assignment operator. And as we did with the list, it's a deep copy of right-hand side is returned with garbage collection. Okay, so it has to clear off the right-hand side. So if you say my tree gets your tree, if you say my tree gets your tree, like this, then what happens is the original my tree is cleared, right? So it has to be garbage collected, and then a copy of your tree. My tree gets a copy of your tree, so that's deep copy. So that's not a cut operation, that's a copy operation. Figure 8.13 shows the constructor for a node. Previous versions of the DP4DS distribution software required a constructor for the binary tree itself. However, now that we are using shared pointers, we no longer need a constructor for the binary tree. The reason is because shared pointers are automatically initialized to the null pointer, and a binary tree has a single attribute _root, which is a pointer to a node. Therefore, when a binary tree is allocated, _root automatically is initialized to the null pointer, and therefore the binary tree is initialized to the empty tree. So figure 8.13 shows the constructor for a node. This constructor has one parameter, data, with one
item in the initializer list, which is equivalent to underscore data gets data. So let's trace figure 8.13 for the statement P gets shared pointer to a node, new lnode t 70. In this example, 70 is the actual parameter, which corresponds to the formal parameter data in the constructor. Part A of the figure shows the initial pointer. When new executes, enough storage is allocated from the heap to store an L node, consisting of underscore left, underscore data, and underscore right. Part B of the figure shows that underscore left and underscore right are automatically initialized to the null pointer. Then the constructor is called, as shown in part C of the figure, at which point underscore data gets data. Then the pointer to the allocated node is returned. In this example, P gets that pointer, and therefore P points to the allocated node.
Now let's take a look. Let's take a look at insert root. So now what's our precondition? If underscore root is not equal to the null pointer, we're in trouble, right? So it has to be. You can only insert. Remember when we did the demo? You can only insert root into a what? Empty tree. Are you with me? So what happens then, it does a throw -1. Otherwise, what happens? Underscore root gets what? New lnode t data, right? So I think I have a picture here. So if you say my tree, so if my tree, now see, my tree in part A of this figure has to originally be what? The empty tree. So if you say my tree.insert root 20, then obviously what happens? Underscore root gets new, da da da. And we saw what that does, right? So what does it do? It does this, part B. Everybody good? So that's how we do insert root. Okay. Now, this next one, figure 8.15, is an example of doing set root. So suppose that my tree has a root of 80, and 80 has a left child of 70 and a right child of 50, and neither one of those have any children. Suppose that's the original tree. And do you remember when we did my tree.set root 10? Now the tree has to be what? Now the tree cannot be what? It can't be empty, and all it does is what? Changes the what? Yeah, so it changes the what to what? The 80 to 10. Yeah, that's all that does. Are we good? So that's the action of set root. Okay, and I don't think I even have the code for that. That's, or do I? Yeah, no, I don't. Okay, so that was a set root. Now, and I think we also demoed set right and set left because that's how we built our trees. Do you remember that? Okay. So, a precondition for, so this is the code for set right in figure 8.16. So set right says if root equals null pointer, so now if it's, how can you set the right of a tree if the tree doesn't even have a right? Yeah? So we implement its precondition by saying if root equals null pointer, we throw -1 with an error message. Otherwise, oh, by the way, you guys, I've noticed on your exams that a lot of people are still writing else here. Do you see why you don't have to write else? Does everybody, but anyway, on your code, do you see that the code, it's like having a return. You know, like when you have a return in the middle of some code, you don't have to do else, because once it returns, it'll return, it'll never get to that anyway. So this is, I think it's nice style to dispense with the else part there. Okay? But if the precondition is met, then what do? We do underscore root arrow set right subtree. Okay? And now let's take a look at the code for set right. And what do? We do underscore right gets subtree dot root. So that makes underscore right point to what? The same thing that what? That makes subtree underscore root is pointing to. Are you with me? And then what? Subtree dot underscore root gets the null pointer. So remember it's a cut, right? So here's the figure.
Figure 8.17 shows the sequence of events that happens when we execute myTree.setWrite yourTree. Now recall that we are in the node version of setWrite, which means that our environment consists of the node that contains 60 as its data. On the other hand, we have been passed yourTree, which is a tree. We have not been passed a pointer to a node. So the first statement to execute is underscore right gets subtree dot underscore root. This makes our underscore right point to the same thing that subtree dot underscore root points to, namely the node that contains 80 for its underscore data. And now we notice that 40, the node with 40, is no longer accessible. That means that the magic of automatic garbage collection takes over and automatically deletes these. Now in previous versions, that had to be done manually by the programmer. But now with shared pointers and automatic garbage collection, the programmer no longer is required to delete that subtree. And then the next statement to execute is subtree.root.reset, which is equivalent to subtree.root gets the null pointer. And that is the completion of setWrite.
And here's operator gets. Now this is exactly the same code as operator gets for the list L1. The only difference is, instead of being copyroot, it's what? What do we have for the list? Do you remember what it was? I think you wrote it. Instead of copyroot, what was it? It was copyhead. I think you wrote copyhead.
Yes.
Yeah. So, but anyway, it's the same code, okay? And then return star this. All right? And now I have written copyroot for you. So here in figure 8.19 is copyroot. So the way the copyroot works is, now, if the right-hand side is empty, then what do we return? Null pointer, right? Otherwise, what do we return? The root version of copyroot. Are you with me? And so now that we're in the root version of copyroot, we know there's at least one node, right? We know that there is at least one node. And so what we do is we do L node T star result gets new L node with the underscore data in it, okay, because this is a root, we're going to copy it, so with data in it, all right? And then if underscore left is not equal to the null pointer, then we call result arrow underscore left gets left copy root, so that's a recursive call to copy the root for the left tree. And then if the right has something that needs to be copied, then we return result gets right. And by the way, if those don't get called, then that node got initialized with null pointers for left and right. See? And then we just return result, and that's it.
We will conclude this recording with a screencast describing methods for removal. There are 3 methods for removal: clear, remroot, and remleaves. All 3 of these are exercises for the student. The post condition for clear is that this tree is cleared to the empty tree. This is actually a simple one-liner. Let's see the effect of executing myTree.clear, where myTree has a root whose data is 60. Is all you have to do is set myTree._head to the null pointer. And then the magic of automatic garbage collection takes over and the tree is cleared. Previous versions of DP4DS distribution that did not use shared pointers required the programmer to manually clear the tree. The next method for removal is remroot. The post condition for remroot is that the root node is removed from this tree and its element is returned. So how can you remove the root node of a tree if the tree has a non-empty left subtree and a non-empty right subtree? What would you do with one of those trees? You can only have one non-empty tree in order to remove the root. So let's see how this works. In figure 8.22a, we have a tree whose root is 30 and whose left subtree has a root of 70 and which has an empty right subtree. So it's easy to remove this root. What happens is the left subtree becomes the new tree. And figure 8.22c shows a tree with 30 as the root and with an empty left subtree and a right subtree that is not empty whose root is 80. So after removing that root, the tree with 80 becomes the new tree. And here is the effect of rem leaves. Recall that the definition of a leaf is a node that has an empty left subtree and an empty right subtree. In this example, the leaves are 90, 40, 50, and 75. So part B of the figure shows the tree after the removal of these leaves. I will end with one tip on how to remove the leaves. It is obviously a recursive procedure, but you cannot be in a leaf in order to remove it. You must be in the parent of the leaf in order to remove the leaf. That's your hint. All right, that's it for now. See you next time. Happy coding.